Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Renata Frelikh with us today. Hello, Renata.
Hi, Frank. Thank you for having me.
Well, thank you for agreeing to talk about your very awesome article, which we will get to here very shortly. And let's see, Renata, what is your geolocation? Where are you at?
I'm located about 15 minutes away from Boulder, Colorado.
Ah, okay. I thought you were going to say 15 minutes from me, and I was going, really? Okay.
No.
Okay. Let's see. And we are deep in winter in the northern hemisphere. And so, is there snow on the ground 15 minutes from Boulder?
No, it is
Oh,
sunny and warm here.
oh my
We
goodness.
haven't had much of a winter. It snowed maybe once.
Wow.
So this seems to be maybe a little unusual. In previous years, we've had snow all the way in May. So I'm keeping my fingers crossed. Maybe things will change. I'm remaining hopeful.
Yeah, yeah. So I'm in Phoenix on this February 12th, 2026, as we record this. And I heard something this morning as I was sort of listening to the news that it was so far, it's been the driest winter on record in Phoenix. And so that would kind of go along with no snow going on around Boulder. So yeah, a little less moisture in the west mid this year. So we shall see. And Renata, what do you like to do for research?
I am a theorist working on exoplanets.
Cool.
So I make numerical models to try to understand how planets form and evolve. I'm interested in both the solar system and exoplanetary systems. And I'm particularly interested right now in how planetary atmospheres evolve through atmospheric escape.
Ah, yes, very cool.
Yes.
And that is going to bring us to this very awesome APJ article. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Efficiency of hydrodynamic atmospheric escape in hot Jupiters and super Earths. And Renata, take us away.
Yes. So this is a paper that I wrote with my PhD advisor, Ruth Murray Clay at UC Santa Cruz.
Hmm.
Um,
Oh,
yeah,
welcome, fellow banana slug.
yes.
I also did my PhD at Santa Cruz.
Oh, wow. Yes, fellow banana slug.
Fellow banana slug. Okay. Well, with that great shout out, here we go. Let's go.
Yeah, so in this paper, I describe the code that I wrote to model atmospheric escape from hot Jupiters, which are
Mhm.
gas giants orbiting their host stars on extremely short period orbits. So less than 10-day orbital periods. Imagine putting Jupiter 10 times closer to the sun than the orbit of Mercury. That's
Okay.
how close they are. Yes.
Okay.
Um, so, a brief overview of atmospheric escape. It's a process by which close in, highly irradiated planets evaporate, potentially losing their atmospheres over the planet lifetimes. This can strip the entire atmosphere of a smaller terrestrial sized planet down to a bare rock.
Okay.
So, planets like Kuro 7b or 55 Cangri E are examples of planets that lost any atmospheres that they had, with the exception of maybe very thin atmospheres composed of evaporated rock. Um, so, the Radius Valley is an observed dip in the radius distribution of planets around 1.8 Earth radii.
I'm with you.
Planets below this valley, they're called super Earths. Their higher densities are consistent with rocky compositions, basically with no atmosphere. And
Mm.
above this valley are the sub-Neptunes, which
Okay.
are planets with a lower density, consistent with a variety of compositions, one of which is a rocky or maybe icy core surrounded by a hydrogen and helium envelope.
Okay.
So it's thought that photoevaporation by the host star may be combined with a process called core powered mass loss, caused these smaller planets to lose their atmospheres because they're less gravitationally bound and it's easier to strip those atmospheres away.
Yeah.
Um, so now, for the larger planets, such as the warm Neptunes and the hot Jupiters, atmospheric escape has actually been directly observed. Stellar extreme ultraviolet, EUV. and
hmm
X-ray radiation ionizes and heats the thermospheres of these planets.
hmm
The heating drives winds of fast-moving hydrogen and helium from these planets.
hmm
And this has been observed with several methods that I list here, most notably through the Lyman alpha and metastable helium absorption.
hmm
So the Lyman alpha emission line from the star gets intercepted by fast-moving hydrogen outflows from the planet, leading to a dip in the brightness during transit. This would be observed with the Hubble Space Telescope, HST,
hmm
and observations of this have to be made in space because the hydrogen in Earth's own atmosphere also emits Lyman alpha, and it just obscures the signal. These observations are pretty difficult to make because the ISM, it turns out, also absorbs Lyman alpha, meaning that we can only really probe the high velocity gas in the line wings of this line.
Okay.
Um, and then another great probe of this atmospheric escape process is metastable helium absorption. It's
hmm
actually accessible from the ground using high resolution spectroscopy, and it can also be detected with HST. Basically, for this, helium is ionized and then it recombines into a metastable state, triplet state, which can absorb the 10,830 angstrom line.
Okay.
So that's another sort of probe of atmospheric escape in transit.
Yes.
Um, yeah, so hydrodynamic escape is this really dramatic sort of bulk outflow of the upper atmosphere of a planet that's caused by energy input from the star.
Okay.
Um, we're interested in how efficient this process is at driving these winds from the planet. So hydrogenic escape is not the only way to remove energy from the system.
Okay.
It can, for example, be absorbed in one layer and then the heat can be conducted downward and that can be radiated away bolometrically from the planet by molecules, for example, at lower altitudes, or it can be radiated away by atomic and molecular coolants. So here for hot Jupiter, for example, H3 plus cooling and Lyman alpha cooling have been identified as very important radiative cooling sources
Mhm.
that I'm going to focus on here a lot in this paper.
Okay.
Um, these cooling processes dominate at different altitudes in the atmosphere, and that's related to where stellar photons of different energies are absorbed.
Right.
Um, yeah, and then for the smaller planets, such as the sub-Neptunes and super-Earths, atmospheric escape, like I've mentioned, can shape the bulk composition of the atmosphere and can have population level impacts, such as the radius valley. Um, but they're also higher in metallicity, so they're going to have additional molecular coolants.
Right.
Yeah.
Yeah.
So
hmm
but in this paper, really the question that I'm trying to address is how efficient this extreme ultraviolet heating is
Yes.
at driving these outflows, and how does that scale with distance from the star?
Mhm.
And at the end of the paper, I will go into sort of my starting to work on pushing the model down to lower masses to the super Earths and the sub Neptunes, which I find very exciting.
Okay. We'll come back to
Yeah,
that. We'll come back
we
to
will
that.
come back to that. Yes. So I think that sort
Mhm.
of brings me to the methods section of the paper.
Slide down. And how are we going to do this? Okay.
That's just the second page.
Did I miss that? Methods. Here we go.
There we go. So in this paper, I created a one-dimensional numerical model of a hot Jupiter undergoing hydrodynamic atmospheric escape as
Mhm.
a result of stellar irradiation. So
Cool.
I say here that we begin by focusing on the hot Jupiter and warm Jupiter regime. And I just hinted in the intro that I'm going to extend this model to smaller planets, such as the sub-Neptunes and super-Earths.
hmm
Um, so the Kepler and TASS samples have detected thousands of these smaller planets in transit, and the population is strongly shaped by atmospheric escape, which again, we've seen from the radius valley. So part of developing this model is really developing a framework for understanding how things like radiative cooling from atoms and molecules can impact these outflows for planets in all size regimes. Um, but here, for the hot Jupiter case, I'm going to focus on a molecular hydrogen and helium composition with solar mass ratios, because that's a good approximation for a gas giant, given that the bulk of its mass is inherited from the circumstellar disk.
Good.
So, launching these winds self-consistently can be tricky.
Hmm.
So, we need an initial condition that's adequate such that the code doesn't have too much difficulty in converging to steady state. These models don't always behave perfectly on the first try. Sometimes you need to try
No doubt.
a different initial condition. For example,
Uh-huh.
um, for planets that are Neptune size and smaller, I was able to start the simulations with an isothermal hydrostatic atmosphere profile, meaning that it's
Mhm.
zero velocity everywhere initially in hydrostatic equilibrium.
Huh?
But for the hot Jupiters, it did help to start with an initial velocity
Yeah.
greater than zero because the gravitational well of these planets is just bigger.
Yes.
Um, so here I've mentioned a snowplow phase. That's a numerical difficulty that arises when the wind has too much material downstream that it has to push out, and the simulation just has trouble. But really, that's an issue with the initial conditions. Maybe they weren't close enough to um, the steady state. Intermediate solutions can
Yeah.
sometimes break. So, yeah. Um, So going down, I am simulating a highly irradiated planet. And for the EV spectrum, I just use solar measurements, which is sufficient for G-type stars. The
Mm-hmm.
problem is that EUV is extremely hard to measure for other stars. It gets absorbed, so it has to be reconstructed from things like that we can't observe, like X-rays or Lyman alpha. There's a planned space mission called Mantis from
Oh, yeah.
LASP here at
Mm-hmm.
CU Boulder
Mm-hmm.
that will actually measure the EUV emission from stars,
Cool.
which is really exciting because that's what directly drives atmospheric escape in these models. So,
Mm-hmm. That was a good
yeah,
theoretical ask. Very good.
yes. Um, So here is a very important point that I want to make, which is when is my model valid? A
Mm.
planet atmosphere can be modeled as a hydrodynamic outflow only if the gas remains collisional up to the sonic point, which is the distance from the planet where the gas velocity becomes supersonic.
Right.
I'm going to talk about the hydrodynamic equations soon, but what I'm really modeling is an atmosphere composed of gas atoms and molecules.
Right.
And I'm not going to be tracing each individual particle path, which is something one might do in a kinetic model.
Cool.
I'm going to approximate the bulk motion of the atoms and molecules as a fluid. So this approximation only holds if the gas is collisional,
Yeah.
meaning that the scale height, so the particles have to collide many times over a scale height. That's the distance over which the atmosphere significantly changes.
Yes.
Um, so we compare the mean free path to the scale height. If it's smaller, then the gas behaves as a fluid. If it's not, then we have to keep track of every particle.
Mm.
So a full kinetic model would capture both regimes in principle, but it's of course not computationally feasible for the modeling we're doing, and it's unnecessary. So we
Right.
use the fluid equations because they're an accurate representation of the collisional regime.
Cool.
Um, and that brings me to the equations.
Mm-hmm.
So equation one, two, and three are the main ones I'm going to talk about
Mm-hmm.
uh, because they're just written in a really nice form. It's my favorite form, the Lagrangian form.
Okay.
So the time derivatives on the left are called the Lagrangian, or sometimes maybe you've heard convective or material derivatives.
Yes.
They represent the time rate of change of a fluid quantity that is moving in a controlled volume through space with the
Mm-hmm.
flow. So the volume itself can expand or contract, but it always contains the same parcel of fluid
Yeah.
as it moves with the flow.
Mm-hmm.
So the first equation is just the continuity equation in Lagrangian form.
Yes.
It says that the density of a fluid parcel changes only if the flow is expanding or compressing. So this divergence of the velocity term, that's your expansion or the compression term.
Mm-hmm.
Um, the second equation is the momentum equation, which is just Newton's second law. The term on the left might look like a mass times acceleration. It means that a fluid parcel accelerates because on the right, the pressure gradient or external forces. The last term on the right is basically just gravity and the tidal force, but I kept it general.
Okay.
Um, the third term is the energy equation. So
Uh-huh.
there are several ways to write the energy equation, but I've chosen to write it here for the specific internal energy E. So that's the internal energy per unit mass. That's just the thermal energy without including kinetic energy. Um, and the terms on the right, the first term is the PDV work term, so adiabatic expansion term.
Mm-hmm.
The second term is gamma, the EUV heating term.
Eating.
And the third term is lambda, that's the radiative cooling term
Uh-huh.
that we're going to focus a lot on in this paper. That includes
Source term.
H3 plus cooling and Lyman alpha cooling that I will discuss later.
Mm-hmm.
And the thermal conduction term,
Mm-hmm.
that just transports heat due to the temperature gradient.
Mm-hmm.
Um, and sort of I put the details of implementing the thermal conductivity in equation 4, and I do some rearranging on the right in equations 7, 8, 9, and 10. But basically, um, I think it's enough to just understand equations 1, 2, and 3 for the general picture.
Okay. Mm-hmm.
I guess I should note that recombination cooling is another term that I didn't include because although it contributes to radiative energy loss, it's just in post-processing, I confirmed that it was negligible, so I didn't turn it on.
Okay.
Um, but in principle, that's something that could matter.
Mm-hmm. Yeah.
Equation
Big
11
bad
is
gas. Okay.
the ideal gas law.
Mhm. Closure. Mm-hmm.
Closure, of course, because we need a way to determine the pressure from
Mm-hmm.
the density and energy.
Mm-hmm.
There are some details here for the calculation of the adiabatic index. I modified it slightly to account for the rotation of H2,
Right.
but that um, is detailed here.
Mm-hmm. Okay.
Um, I want to talk a little bit about in section 2.2 how we set the lower boundary temperature. It's set by the balance between bolometric heating and cooling. So I'm sort of just doing a very simple model of the base. It effectively sets the lower boundary temperature to the planet's equilibrium temperature.
Yep.
And the lower boundary, it's just the region where the atmosphere is beginning to be optically thick to the EUV.
Correct.
Um,
Okay.
so the balance is just shown here. It's a very coarse model that just basically forces the temperature to be, um, for my fiducial planet, 1,000 Kelvin. At
Mm-hmm.
the base,
Right.
then I talked a little bit in section 2.3 about the H3 plus molecule, which is a significant coolant in the thermospheres of giant planets. And it's produced from my chemical network. Basically, molecular hydrogen, H2, is going to be ionized and it reacts with itself to form H3 plus.
Mm-hmm. Yeah.
Alternatively, H2 can react with H plus also to form H3 plus. So those are kind of the two
Right.
pathways. And
Production and destruction. Yes.
production and destruction. So the
Mhm.
destruction happens by recombination with electrons with two branches over here. So electrons destroy H3 plus. And H3 plus emits in the infrared. Um, And equations 13 and 14 are just the cooling functions that I use that depend on temperature. It's just an LTE cooling rate. They're just fits to,
Got it. Hmm.
yeah,
Okay. Polynomials.
um,
Mhm.
polynomials.
Yeah.
The emission is
Mhm.
optically thin, um, meaning that it can escape the simulation domain. Whether it escapes up or down, where it is absorbed by the bolometric layer and radiated away as a black body, I treat it as having left the domain. So
Okay. Okay. All good there. I'm with you. Hmm.
moving on to the other important radiative coolant, Lyman alpha cooling. It's
Hmm.
actually dominant in a lot of cases. It happens where the neutral hydrogen gets excited collisionally in our model by electrons to the n equals 2 state,
Yeah.
um, and it radiates and de-excites. So Lyman alpha photons are actually optically thick, meaning they don't immediately escape to space. They actually scatter and escape from the gas after scattering into the line wings of the Lyman alpha line, which is shown in the appendix with a Monte Carlo calculation, but I'm not gonna go through it here. But
But you should
we
check it out,
did,
people. But you should check it out.
yeah, check it out. It's cool, but we post-processed this to actually numerically show that I think it was about 90% of the photons actually escaped.
Yeah.
Yeah.
Okay. I'm with you.
Hydrodynamic solver,
Mhm.
the advection solver that we use is the constrained interpolation profile scheme, which
Yep.
is good for minimizing numerical diffusion. It's described in detail in Appendix A.
I'll say there's another 40
Sometimes,
equations there.
yeah. Sometimes numerical schemes introduce artificial diffusion that smooths out gradients and profiles just due to the interpolation that you use, and that might cause violations of energy conservation, for example, or mass conservation. So
Like, like,
this scheme sort of deals with that.
mm-hmm.
And
And
I use operator splitting for the other terms.
okay. All right. I'm with you. Okay. So we got our method.
Let's move on to the grid in figure one. I think just looking at the grid is best. Here's a picture of the grid. It's a staggered grid. So density and energy live on the regular grid, and velocity lives on the staggered grid.
Yes.
It's convenient because the velocities at the cell centers line up with the boundaries of the regular grid cells. So whenever you have gradients, um, it's just convenient. I ended up
Uh-huh.
putting this figure in the paper because I kept having to redraw the grid every time when implementing the numerical methods. And I thought, okay, I'll just make the figure and put it in the paper.
Make one. Let's see.
Yes.
And how about the black boxes? What are those?
The black boxes, they're not actually cells. So that's just empty. The staggered grid starts out slightly staggered from the
Okay.
regular grid. So the gray white boxes are the ghost cells, and I've only represented one grid cell here for the regular grid, but you can imagine just extending this grid for, 1,000, a million grid cells, whatever you like. I mean, yeah. Um, this is
Okay.
just kind of one cell.
Uh-huh.
So I'm going to have n cells for the regular grid and n plus one for the staggered grid. And
I'm with you.
yeah,
Mhm. Good. Hmm.
this also helps to prevent oscillations arising from odd even decoupling
Correct.
if you have a non-staggered grid. So it's really nice. All of the cells are coupled to each other. The velocity grid is coupled to the density grid in this way.
Okay. All right.
Artificial viscosity,
Docs. Docs.
this term here in equation 16
Mm-hmm.
is a Zeus-like viscosity term. So the code Zeus uses something similar to this. Its
Yes.
purpose is to stabilize the solution if it encounters a steep jump
Mhm.
and things like pressure, for example. Otherwise, you might get numerical oscillations or wiggles. It's a
Mhm.
very technical term.
Yes, wiggle.
Um, yes, it is only turned on when I have compression.
Okay.
So
Yeah.
it's like an extra
Yeah.
repulsive pressure in regions of compression. It spreads the discontinuity over a few grid cells so the code can resolve it smoothly while dissipating some energy as heat. So this doesn't affect the steady state solutions that we find here
Right.
because there's no compression in the steady state. It only helps the code evolve to steady state. If there are any potential discontinuities or shocks that might arise
As the calculation moves along. Yep. Hmm.
as it moves along. Yes.
Okay. And so we got that. How about some boundary conditions? Hmm.
Boundary conditions. Let's start with the outer boundary conditions. So,
Okay.
physically, in a supersonic flow, you don't have to actually impose boundary conditions at the outer edge because information can't propagate upstream.
Hmm.
You do still have to be careful sometimes for numerical reasons, not necessarily physical reasons. If you include diffusive terms and treat them implicitly, but we're not
Okay.
dealing with that here.
Okay. Okay.
So, if you expect hydrodynamic escape, it's very important not to impose a fixed outer boundary condition,
Uh-huh.
such as, for example, a gene's escape rate, because essentially you're not allowing the atmosphere to freely evolve.
Right.
If the atmosphere is truly not escaping hydrodynamically, so it doesn't evolve to a solution that's transonic and collisional at the sonic point, then you will need a kinetic model, and you can't use the fluid model. You
Good.
can model Jean's escape that way, and then
Hmm.
Jean's escape is when just the high velocity end of the thermal distribution of particles escape from the planet in a particle by particle and not in a fluid way.
I'm with you.
Yeah. So
Okay. Good.
outer boundary, inner boundary conditions, I
Hmm.
basically impose the densities in the temperature. I talked a little bit about the temperature earlier, and I leave the velocity as a free parameter because I need to allow waves to leave the domain sometimes.
Yes.
Otherwise, you get wiggles.
Bang, bounce, bounce.
Um,
Yep. Hmm.
yeah.
Uh-huh. Yeah, we got a network.
Chemical network. Yes.
Mhm.
So I include a chemical network with photoionization of hydrogen and helium. So table one shows the chemical network. I only include hydrogen and helium reactions.
Mhm.
You can see, um, I guess reaction eight is important because that's the one that forms the H3 plus. That is the important infrared
Okay.
coolant.
Yes.
Um, and there's also thermal dissociation of H2 that's included somewhere here. Reaction 12. I think M is just a, like if you're ever confused, M is a collisional partner. It's just any atom or
Anything.
molecule.
Okay.
It doesn't get used up in the reaction. So
Mhm.
you, it's just a collisional partner.
Like a catalyst.
So it's, yeah, it's like a catalyst. I was trying to figure out the difference between that and a catalyst at some point. There's some kind of chemical technicality. Uh,
Okay. Okay. And
yeah,
zero
like a
authority would just
catalyst
call it
can even
catalyst.
be a surface.
Yeah, yeah, yeah,
Yeah.
yeah. Okay. Hmm. Okay, very good.
Um,
So we got 22 reactions in this network.
yeah, which is a very short network, actually. As I've learned, people can have hundreds of reactions.
Yes.
Yes. Um, but this is setting the stage for adding more reactions
Oh
and
yeah,
more
yeah. No, I,
complicated
I,
chemistry, which I'm very excited about. Yeah,
yeah, yeah.
uh,
Got to it starts somewhere. So good.
exactly. So 2.10 spectrum. So I guess equation 17, that's the optical depth. Ionization is calculated using the optical depth from the top of the planet downward because you're irradiating it from the top. That accounts for absorption along the line of sight, where optical depth it's defined in equation 17.
Okay.
Figure two, I've sort of, it's not,
Hmm.
it's just a schematic where I've drawn the flux that's coming from the left and it hits this cell that contains helium, molecular hydrogen, atomic hydrogen, and it sort of
Uh-huh.
absorbs the incoming flux, and then the stuff that comes out as the initial flux times e to the minus tau in the cell. So
Mhm.
attenuation happens within a cell.
Yes. Good. Okay.
Um,
I'm with you. Mhm.
yeah, I just in this section, sometimes the cells can be optically thick, in which case you should distribute the ionizing flux between the ionizing species to make sure you're not double counting the flux.
Okay.
If it's optically thin, there's plenty of flux to go around, so it's sort of determined by the cross-sectional area.
Yeah.
Um, but that is what I sort of go through at the end of this subsection. And I'm gonna
Okay. I'm with you.
uh, I talked about how I calculate the reaction rates and rate coefficients for the photoionization reactions, which I then use in table one. So just numerically implementing it, it's just like an extra reaction with one reactant. For example, K1 is H,
Photon.
and the rate coefficient is just given by the
Mhm.
equation in, equation 21 or something.
Mhm. Okay.
Yeah.
Do that. Okay.
And I,
Right ionization. Yes. Okay.
yeah.
I'm with you. hmm Following along.
So I can move on to the secondary ionizations due to the high energy electrons, 2.11. So that's actually pretty interesting. High energy photons can produce energetic photoelectrons when
Ooh,
they
right.
ionize hydrogen or helium.
Right.
So these electrons are now high energy and they can go on to collisionally ionize or excite or dissociate additional um, species in the gas until they finally lose their energy with collisions with other electrons, for example, and thermalize. So there's this high energy electron population
Right.
that's going to increase the ionization fraction in the gas primarily. You end up with more than one ionization per photon. And I account for that here using the results of Monte Carlo model by Delgarno et al. For a mixture of hydrogen and helium. So
Mhm.
there's various things that can influence the number of ionizations that you get. And I quantify
Mhm.
that here with the
Mhm.
um, various expressions here, and that depends on the ratio of H2 to H and the ionization fraction and
Yeah, the energy.
the
Photon.
energy, of course, yes. And
Okay. hmm
yeah, we sort of had to go through here and decide or determine what excitations are going to be thermalized and which ones are going to be radiated away. So that depends on your density and
Yes.
yes.
Okay.
So that's accounted for here using this sort of tables that I look up.
Got it.
It would be interesting to actually implement this.
Uh-huh.
Yes. Um,
But for now,
but for now, yes, this is sufficient for now. This is good.
right.
Um,
Good. I am. Okay. The heating. Dun, 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 dun. Okay. I'm good. hmm Okay. And mean energies. Okay. Takes a lot to do these secondaries. hmm
yes.
More excite them up. Yes, quite a bit. Okay, and we do some vibrational stuff as well. All right. Yes, there we go. Okay.
So this um, first, it increases the ionization rate.
Yes.
So there's an additional in implementing it, the sort of additional rate for ionization and the rate coefficient. And also this decreases the heating efficiency. So equation 35, for example, is a heating efficiency term.
Okay, let's go down. Did I miss that? 35. There we go.
Okay,
Right there.
yeah.
I was on it. Mm-hmm. Okay, bum, bum, fractional. And then we got those two terms which were defined over there. Okay, good. Mm-hmm. Cool. A lot of work for secondaries. Okay. Maybe section 3, table 2.
Yeah, let's move on to the results. I think I can talk about the fiducial hot Jupiter that I'm simulating. So it's a planet of about zero point 0.7 Jupiter masses, which is it's the case of HD 209458b,
Okay.
basically.
Mm-hmm.
I'm saying it's orbiting a solar mass star
Yes.
with a radius that's slightly inflated to Jupiter's at a semi-major axis of zero point zero 0.05 AU,
Close.
1000 degrees. Um, yes, very close. 1000 degrees Kelvin.
Mm-hmm. Mm-hmm.
Yeah.
Okay. Good.
And I'm using the solar spectrum that I described
Right.
before.
Cool. Okay. So
So I would
Jupiter
like
goes.
to,
Uh-huh.
maybe I'll go to the figures. I think it's easier to describe this.
Okay.
Um,
So we've got it set up. We've got all our conditions, and let's see. Turn the crank.
maybe figure 3.
Uh-huh. And let's see what we got.
Yeah, these are the results. This four-panel plot displays the density, velocity, pressure, and temperature in the wind. So panel B on the right top displays the velocity of the wind as a function of altitude, so radius here. Um, it
Right.
reaches 8 kilometers a second at the sonic point, which I've marked here with the red X.
Yes. Mhm.
I think the temperature is interesting. The bottom right, it starts out at 10 to the 3 Kelvin at the base and it quickly heats up to about 10 to the 4 Kelvin.
Okay.
That's where Lyman alpha kicks in, Lyman alpha cooling, and it can start cooling the gas.
Uh-huh.
This is a thermostat effect. It keeps the temperature peak to 10 to the 4 Kelvin.
Yes.
It can only kick in when it's hot enough, but it prevents the gas from getting too hot.
Mm-hmm.
So finally, if I go higher in altitude, the temperature drops due to the PDV sort of
Yeah.
cooling the outflow expansion.
Mm.
Yeah.
So
Um,
I'm starting to get a sense there's going to be layers here. Mm-hmm.
layers, yes. Um, I'm going to scroll, maybe we can scroll down to figure 4 to look at the composition.
Sure. Ooh, always a good thing to do. Compositions.
Yeah.
Okay.
It's the composition of the atmosphere, the upper atmosphere with altitude. So the on
Yeah.
the left is a zoomed in to the base plot, and the right shows the larger scale outflow. It's just so you can see the details of
Mm-hmm.
the um, molecular hydrogen layer that you can see in green. H2 sort of drops off at 1.04
Yeah.
times 10 planetary radii.
Mm-hmm.
So this layer contains the H3 plus that I plotted here in red.
Yeah.
It's our important infrared coolant. So
Mm-hmm.
there's not a whole lot of it, but it still contributes significantly to the cooling. It's interesting. Um, from the chemical network, we saw that ionized molecular hydrogen, H2 plus, which is plotted here in purple. It
Oh.
reacts with the H2 to form the H3 plus. So actually the photons have to be able to reach the molecular hydrogen layer to ionize it in order for the H3 plus to form.
There you go.
Like it can't be shielded by something else above, so something has to let it form. I call this the H2 layer because H2 is present there and because reactions with H2 happen there, not necessarily because it's the main species,
It's
as you can
dominant.
see
Right.
here.
Right.
It actually transitions to atomic, especially like as you move
Sure.
a little bit and higher in altitude, you know from the temperature plot that the temperature rises steeply. So that's where you get the thermal dissociation of H2.
Cool.
And this is like the blue line, the blue solid line
Mm-hmm.
here. That's the H.
Mm-hmm.
Um,
Mm-hmm. And
that's the atomic layer. It's what I call the atomic layer because it's the source of our other radiative coolant, Lyman alpha cooling,
okay.
which happens again from the excited atomic hydrogen. And this cooling thermostat's the atmosphere to 10 to the 4 Kelvin. And
Mm-hmm.
then moving higher up in panel B, we have a wind consisting of ionized atomic hydrogen. So the dark blue transitions into the light blue, and it's very ionized here. There's neutral is still a
Oh,
component
good.
here, which is
Yeah.
what we observe through Lyman alpha transits, for example, but actually most of the outflow is going to be ionized here.
Okay.
Um,
Okay.
and yes, so always in post-processing, we verify that the mean free path to collisions is less than a scale height for the entire outflow, or at least like at the sonic point, but here it's for the entire outflow,
Okay.
meaning that the gas is collisional and it's okay to model it as a fluid.
Cool. Very good. That's
Um,
okay. Good. I'm with you. Mm-hmm.
so figure 5 is the
Mm.
energy balance plot in the
Mm.
atmosphere. So I always like to follow the energy, and that's kind of the whole goal in this paper to
Okay. Heat and cooling rate.
determine what happens to the energy. How efficient is the EUV at driving the outflow? So I
Mm.
just want to say, so this is kind of the similar form where the base is on the left, it's zoomed in, and the right is zoomed out.
Uh-huh.
Um, the shaded region in white at the base is just that boundary condition that I talked about earlier, where I have a balance of volumetric heating and cooling that sets the temperature to 10,000 Kelvin.
Right.
Um, so that's the region that's optically thick to the EUV. So it's not strictly valid, or it's a coarse model of the base.
Mm-hmm. Right. That's a better way to say it.
Yeah,
Right.
yeah. It's just the boundary condition.
Uh-huh.
Um, so here in this plot, I'm plotting the magnitudes of the heating and cooling rates as a function of altitude. Um, the incoming EUV absorption is plotted in blue. So that's just the sum of the spectrum from the star hitting the planet.
Uh-huh. Uh-huh.
Then we have total heating from the EUV. That's the dashed black line. It's bolded.
Mm.
So what happens is that the energy from the photo and secondary, or the heating is okay, the dashed black line is the heating from the photo and secondary electrons that is thermalized as opposed to overcoming the ionization potentials of
Yes.
the gas species. So the
Mhm.
difference between the solid blue line and the dashed black line goes
Uh-huh.
into ionization mostly.
Uh-huh.
Um,
Okay.
there are some details with the implementation of the secondary electrons where some of the energy can actually be radiated away, but that kind of is all taken care of here. So everything dealing with the secondary and the ionization potentials
Drives this difference. Okay.
drives this difference exactly.
Mm-hmm.
So the difference is pretty significant here,
Yeah.
especially at the base where the higher energy photons are deposited. So
Order of
as
magnitude.
we've
Mm-hmm.
as we've seen that, I mean, the higher energy photons are the ones that are most affected by the secondary effect, where they could just result in a bunch of ionizations. So that makes sense.
Mm-hmm.
A lot of models just assume an efficiency factor or omit it entirely. So
Right.
this is a slight improvement based on that. Um, using the results of their Monte Carlo model. But my composition is also limited to hydrogen and helium.
True.
So
Okay.
we need better models of that, or I need to write a module for that if I'm going to include more complicated compositions. But sometimes this way of parameterizing it is sufficient.
Hmm.
Sometimes,
Sometimes simpler is
um,
better.
yeah. Um,
Mhm.
but this is important, especially if you include X-rays. Yeah,
Yeah. Uh-huh.
yeah,
Yes.
yeah, yeah.
Okay.
So now
Those are all done. Okay. Mm-hmm.
the black dashed line, that the UV heating,
Mm-hmm.
and the gray advection line. So there's two gray lines.
Uh-huh. Yes. Yes. One here, one
The
here.
solid one results in carries away energy, so it's like a minus energy term, and the term on the dashed advection line, the dashed gray line, is sort
Mm-hmm.
of like a heating term. Basically, you're bringing in energy from
Yes.
somewhere else. In this case, from deeper in the out, deeper in. Um,
Mm-hmm.
so that sort of serves as an energy source here. But
Right.
if you so the advection and the EUV are balanced by the cooling terms because we're in steady state. So I'm going to go
Right.
through the cooling
Right.
terms. The first one is the outflow itself, the adiabatic cooling, the PDV. That's the green solid line.
Yes. Mm-hmm. So it
You
goes.
can see it dominates in the outflow.
Yes. Uh-huh.
And maybe it's offset by various things on the
Definitely.
left in the base.
Definitely.
Um,
Uh-huh. Yes. I'm with you. Good.
Now, in red, the cooling term plotted in red is the H3 plus cooling.
Yeah.
It's not dominant here, but it does become more important as you decrease the stellar flux. So as
Mm.
you move the planet out in the grid of models that I'm going to show later on, it becomes more important.
Okay.
Um,
All right.
Now I'm going to move up in radius slightly from the H3 plus. And you
Mm-hmm.
see this purple line, that's
Yep.
the Lyman
And
alpha
that flow.
cooling rate.
Oh, funny they pick up right there.
So it actually dominates over the PDV cooling. It
Yes.
radiates away most of the energy deposited here.
Purple over green.
Um,
Mhm. Cool.
then
And it drops off.
Going back to the heating term,
Okay.
the UV heating, that's the dashed black line. It's actually coming from a spectrum, so it can be decomposed into energy bins. And where specifically in the atmosphere the photons are deposited depends on their energy.
Yes.
And what I found is that, um, as you might expect, the highest energy photons are deposited further in
Yep.
due to their smaller cross sections, and intermediate energy photons are deposited in the middle, kind of within the Lyman alpha cooled region, and
Hmm.
photons closer to the 13.6 eV, so the ionization threshold of atomic hydrogen, they're deposited towards the outflow region where the PDV dominates.
Yes.
So
Cool.
different cooling processes happen at different layers in the altitudes, and they offset different photon energies.
Yes. Makes
Um,
sense. Hmm.
and yeah, so we've seen that a lot of the incoming flux is either going into ionization or radiative cooling. So there's a decrease in efficiency there. Um, Not all of it is going into driving the outflow.
Cool. Hmm.
And I'm not gonna, so figure six just shows what I've just described with the different energies. I think it's, if we scroll down a little bit, it's the
Oh, yeah.
same
Yeah, yeah, yeah.
heating and cooling plot. It's the same plot, just I've zoomed in to show the tau equals one surfaces. So where does the energy deposition peak for photons of different energies? So these
Right.
numbers are just, 165 eV or 15 eV. So there's sort of a
Uh-huh.
trend with decreasing photon energy as you move up in the atmosphere.
Uh-huh. Okay.
Yeah.
Cool.
Um,
Good.
Different
Good.
photon energies are deposited in different
Uh,
altitudes.
This
Uh,
one. Okay, this is farther out. All right, same format, AB. Okay.
yeah, yeah.
Okay, very good. Cool. Makes sense.
And I'm going to scroll probably let's
Okay. Where would you like to go?
maybe I'll scroll past figure 7, which plots the reaction rates involving molecular hydrogen, and um,
Skip 7, head to 8.
probably we can skip 8. That's the reaction rates involving
Ooh,
atomic
beautiful.
hydrogen to figure 9, which is really the summary
I like this one.
of the model. Yeah, I made this diagram to sort of visualize what is happening here, or this is the outcome of the model,
Hmm.
where we have these different layers that we've identified um,
Yeah.
after running our code. So we can start with the inner layer on the left.
Okay.
So that sort of curved line with the dots, I tried to represent maybe dust or molecules that set the
Uh-huh.
bolometrically heated lower boundary condition. So
Yes.
that's kind of where we start. And then going up, we have this H2 layer, the molecular hydrogen layer that's cooled by the H3 plus, where the highest energy photons are deposited.
Yes.
Um, so it's sort of like aligned the spectrum that I use
Oh.
to, yeah, so
Mm-hmm.
that it matches these layers.
Yeah,
So the
okay.
highest
Okay. Now I
energies,
okay. I wondered why you made
yeah,
it that size.
yeah,
Now I
yeah.
get it. Now I get it. Okay.
So
Mm-hmm.
the highest energies go into this molecular layer. And then,
Okay.
yes, a lot of energy goes into the secondary ionizations here as well.
Yeah.
And then moving further up, this purple Lyman alpha cooled layer of
Mm-hmm.
where the atomic hydrogen is dominant.
Mm-hmm.
Um, Lyman alpha sort of scatters because it's optically thick. So it every time it scatters, it has a probability of being scattered further out into the line wing where it's actually optically thin and escapes. So after some number of scatterings, it can escape.
Cool.
Yeah.
Okay.
And photons that are in the intermediate range of the spectrum, so maybe less than 55 eV, but more than about 15,
Right. Right.
are deposited here and really like offset a lot by the Lyman alpha cooling. Lyman alpha is significant. Um,
Hmm.
then moving further up is the outflow layer cooled by the PDV.
Yes.
Photons around the ionization threshold of atomic hydrogen are deposited here. So here's the sort of ionized outflow. H plus is dominant.
Yeah.
Out to the sonic point at about 3 planetary radii, all
Okay.
the way out to, I've shown the Hill radius.
Hmm.
And then finally, at some point, the outflow is no longer collisional, and that's called the exobase,
Okay.
where you have sort of particles escaping
Uh-huh.
particle by particle, where it's no longer a fluid.
Right. Kinetic. Okay. Nice.
Exactly,
I like
kinetic.
I like this one. Very good. Okay. Beautiful.
Moving on, if you're interested in how the energy, like for each energy bin, if you're interested in the energy balance with altitude, you can look at figure 10. Just that all I'm going to say is that the highest energy photons, you could kind of see in more detail how, for example, on the left panel, the H3 plus kind of offsets some of that. And then for the lowest energy photons, of course, because they're absorbed so
Uh,
much higher up than the molecular hydrogen layer, there's no chance of them. to
Yeah.
be affected by the H3 plus at all.
Right. Okay.
So
I like this little breakdown.
H3 plus cannot shut off the outflow because there's always things absorbed above it.
Yes.
Um,
Very good.
so you can kind of see it here. I've picked three representative energies. So kind of the highest energy, and then something that is in the Lyman alpha, kind of the atomic hydrogen layer, the
Uh-huh.
55 eV that's representative and close to the ionization threshold on
Yes.
the right.
Sort of each of those layers. Uh-huh. Good.
Yeah.
Uh-huh.
Um,
Okay. Cool. I'm with you. Hmm.
why don't we go into the grid of models?
Okay.
I want to talk about what happens to the mass loss when I run a grid, moving the planet, this fiducial planet, away from the star. So I varied the distance
Yes.
from, well, I moved it slightly closer in actually to 0.015, where tides are going to be really important, all the way out to
Mhm.
0.3 AU, where you're still going to see outflows.
Yeah.
And basically, by varying the distance, I vary the flux because it scales as distance squared.
Right.
So
Mhm.
tidal gravity, yes.
Check out Appendix C. Okay. Good.
Yes.
Good. Let's take a look at figure 13.
Figure 13. Yes, I would like to look at figure 13, which shows the four panel plot
Oh,
that you've seen
yeah.
before with the density, velocity, pressure, and temperature, but this time
Figure 3.
for the grid of models, so kind of color coded by distance, with the closest in planet experiencing this dramatic velocity, kind of almost tidally being very affected by the star because it's so close in.
B.
And the sonic point sort of tends to move out. Um,
Trend, yes. Uh-huh. Good.
yeah. Uh,
Why do we truncate a little bit at the closest one in? Pressure truncates, density truncates, temperature truncates.
oh, the truncation. Yes, it's
Yeah.
because I didn't actually need to simulate that far because the sonic point. So I
Oh,
choose
okay.
the outer boundary distance to be far enough that it doesn't numerically affect anything. So
Yeah.
one of the things could be the sonic point is just within the simulation domain, or the hill, maybe the hill radius could be another point, or the
Yeah.
exobase, you know. So the farther out my sonic point is, the farther out I have to simulate.
Correct. I'm with you then.
Yeah.
Okay. A little bit of efficiency there, we'll call it. Okay. Very good. Cool. Okay. That's the equivalent of figure 3.
Yeah. Um, so figure 14
Okay.
plots the relative importance. We'll focus on the panel on the top.
Okay.
So that's the relative importance of the various cooling terms as we vary the distance, the semi-major axis
Uh,
um,
great.
of
Okay.
the planet from the star. So
Okay.
the PDV is the blue. You can see it becomes less important as we move out.
Okay.
Well, the pink is the Lyman alpha and the orange is the H3 plus.
Yeah.
So
All right.
both of these, the radiative coolants sort of increase in importance as you move out,
Huh.
with the PDV going down.
Um, okay.
So you can say it becomes less energy limited as you move
That's a good way.
out.
Right.
Um,
Hmm.
so maybe I should comment, or I should go over a little bit about what energy limited means. It's just a quick
Sure.
um, equation 40,
Yeah.
the
That's
energy limited approximation. It's
a good equation. 40
widely used,
and 40. Hmm.
yeah, widely used in the literature to estimate planetary mass loss rates.
Okay.
Um, it's just a statement of conservation of energy. So this formula relates the energy absorbed in the cross-sectional area pi r squared
Okay.
by the planet to the energy going into lifting the gas out of the gravitational potential well, GM over R. So this is the mass loss rate that you would get if you were irradiated with a flux FXUV um,
Mm-hmm.
for a planet of mass MP and radius RP. So the
Mm-hmm.
radius sets first the cross-sectional area of absorption and also how far away from the planet um, you're taking the gas and trying to lift it. So
Okay. Mm-hmm.
it has a steep dependence on planetary radius.
Indeed. The cube.
Yeah. Um,
Let me
we
grab.
can
Mm-hmm.
maybe look at the, if we scroll up a little, figure 15.
Okay.
Um,
Checking that out. Okay. Figure 15. Okay. And yeah. M dot.
Here's where I compare the mass loss rates for my grid of models that I run for slightly different parameters. I'll explain what they are. I compare it to the energy limited expression.
Mm-hmm.
So on top, I've turned off radiative cooling and conduction.
Yes.
So the orange line is my model result, and the black dashed line is the energy limited mass loss rate, with an efficiency of about a half to account for just ionization losses. So it just
Okay.
scales with distance. Radiation is Radiative cooling is turned off. So you expect this to scale nicely like this,
Oh,
and it does. So that's encouraging for my model.
yay.
It matches the expectation.
Right.
Um,
Good
Now,
justification.
below, you see the mass loss rates for my model with radiative cooling turned on. That's the green dashed line.
Okay.
And the solid pink line. They actually overlap, but I've turned on conduction or
Mm-hmm.
turned it off, but they
Mm-hmm.
overlap here. And I compare it to the energy limited rate. So the
Black
dot
one.
or the black solid line
Right.
plots the energy limited approximation with an efficiency of zero point 0.1, about zero
Mm-hmm.
point 0.1 to account for ionization um, and radiative losses. And the yellow dashed line, that's the same thing, but just with a correction factor to account for tides as you move the planet closer into the star. So
Mm-hmm.
they start out at the same place at 0.3 AU, and you can see them diverge as you go closer in. So
Ah,
that's the same
right.
expression, just
Yeah,
with
yeah.
the correction factor.
Right. Right. Or differences, right. Okay.
So we're comparing the model results to the energy limited approximation. So you can see
Uh-huh.
close in that doesn't completely match because actually some radiative cooling kicks in and you get less mass loss than you would expect. Um, then you sort of go follow the semi-major axis out. Maybe it scales nicely out to 0.05 AU, and then um, radiative cooling starts to dominate more as you go further out. You
Right.
depart from this energy limited scaling, like we've seen.
Right.
You might expect this from the plot where we've plotted the relative importance of these various cooling terms. So PDV does decline in importance.
Right.
So
Okay.
yeah, even for hot Jupiters, the energy limited scaling is only good for a small, I would say a small parameter space,
Small
but really
window. Small
a small
window.
window. Yes.
Otherwise, you can be off by order of magnitude.
Mm.
Good.
So the pink line, that's where I turned on conduction.
Mhm.
So I might expect this to decrease the mass loss rate. So what happens is that heat gets conducted downward toward the base, where it's radiated away instead of powering the outflow.
Oh,
So
okay, Wallace. Mhm.
yeah. I don't see significant difference in these runs, but it's worth extending to lower fluxes. But at that point, the outflow might just be insignificant. So
Yeah.
yeah.
Mm-hmm. Okay. All righty.
Um,
I'm with you.
Figure 17 plots
All right. I get it.
Yeah, so why don't we move on to section 4, which
Yeah.
are the super Earths and sub-Neptunes.
Ooh, yes. Okay.
Yeah, so these are planets that are between the size of Earth and maybe 10 Earth masses, with radii ranging from about zero point 0.3 to 3 Earth radii. In contrast to the hot Jupiters, atmospheric escape can shape the bulk properties of these planets, making this problem more exciting.
Cool.
For example, with the radius valley that I've talked about earlier
Uh-huh.
at 1.8
Oh.
Earth radii.
Hmm.
So an important point is that super Earth atmospheres or sub-Neptune atmospheres are expected to be metal enriched compared to hot Jupiters. You
Yeah.
think of all sorts of planets, such as a water planet or a CO2 enriched planet. This paper only shows results with a hydrogen and helium composition, so the
Uh-huh.
classical kind of
Mhm.
primordial atmosphere around a bare rock.
There you go. Okay.
Figure 20
Yeah, let's look at 20.
shows
Yeah, we've seen these before. Okay.
the familiar four-panel plot,
Okay.
um, which again shows the velocity
Mhm.
flowing through a sonic point, and the temperature plot. I think it's interesting because we
Yeah,
can see that it never gets hot enough for the Lyman alpha cooling to kick in. So
right.
in this case, it's never important.
Uh-huh.
So H3 plus in this model is going to be the only source of radiative cooling.
Cool.
Um, and the temperature is not going to be hot enough to abruptly dissociate the molecular hydrogen.
Mm.
So
Okay.
this is because the planet is lower mass and it's easier for the PDV to just start cooling the gas.
Yeah.
So you're going to see, if you scroll down a little to figure 21, that
Yes.
the molecular hydrogen, the green solid line, it's present throughout the outflow.
Two,
The
yes.
molecules here, yeah, they're not thermally dissociated. The
Mhm.
red line is the H3 plus, so it's present throughout the outflow as well. So
Then,
this, I think this is interesting because looking
okay.
forward, when I look at an
Yes.
increasing metallicity in these planets, this might
Yes.
mean that molecules such as water, CO, CO2, or their various products can survive, contributing to radiative cooling.
Yes.
It's also important to note that molecules can be photodissociated, so
Mhm.
they just have to be present in sufficient quantities, and in a place where UV energy is absorbed to affect the outflow.
Okay.
Um, yeah, so we've seen that for a hot Jupiter, escape becomes a lot less energy limited as we move the planet away from the star in
Yes.
our grid. For
Mhm.
a super Earth, it becomes interesting again because the radiative cooling from molecules becomes important due to their lower temperatures.
Yes. Okay. Mm-hmm.
Um,
Okay. Do. Bum, 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 bum. There we go.
yeah, so this is just a
Mm-hmm.
familiar heating and cooling plot where
Uh-huh.
don't see any of the Lyman alpha cooling at all and H3 plus cooling. Although
Right.
it
Didn't show it.
peaks at the base, it is present throughout the outflow. Um,
Okay. Mm-hmm. Yeah.
and oh yes, I guess table 3, I should mention that this is for just a fiducial super Earth, not any particular planet out there of
Sure.
about 7.2 Earth masses, 1.9 Earth radii. So I picked something to the right of the radius valley, highly irradiated, close to the
Right.
host
Right. I see.
star.
Very good. Yes. The base. Okay. Cool. Very good.
So molecular cooling, definitely very important for these sorts of planets looking
Oh,
forward. Um, Section 5, the discussion, factors like the stellar wind, planetary magnetic field, and radiation pressure can all impact hydrodynamic escape in some way. So, for example, if the combination of the stellar wind dynamic pressure, thermal pressure, and magnetic pressure becomes comparable to that of the planetary outflow, then the outflow can be
yeah.
shaped.
Hmm.
redirected. I'm just comparing scales here, of course, but
Hmm.
it's a useful sort of order of magnitude thing.
Yeah. Right. Always a good
Um,
thing to do. Mhm.
yeah,
Mhm.
radiation pressure might play a role farther out from the planet, and when the outflow is significantly neutral, because radiation, the Lyman alpha interacts with the neutral hydrogen. Um,
Yes.
and a planetary magnetic
Okay.
field certainly can play a role in shaping these outflows if they're significantly ionized. Um, of course, because it's not going to work on the neutral component. But
Sure.
the magnitudes of these fields are currently unknown. So this is definitely very interesting, nevertheless. Um,
Hmm. Hmm. Yeah, well, it's
certainly.
just sort of a rough scale.
Yeah.
Okay, good.
Um,
I'm with you. Okay. All right. What are we got? We were doing okay. Bump-a-doop. Okay. And
I think if we just scroll down,
okay.
there's some literature context that I just wanted to acknowledge the previous work that's been done on this. So Garcia
Always a good
Munoz
thing to
and
do.
Yell created very similar sort of one-dimensional time-dependent models of hot Jupiters that sort of both found sort of the same general
Hmm.
ideas.
Yes.
Yell identified that the H3 plus ion was very important in terms of the radiative cooling. Um, yeah, and Ruth Marie Clay, my advisor, this work kind of builds upon that model, of course. The hot Jupiter understanding.
Good.
Koskinen, the H3 plus work, and yeah, oh, metal line cooling certainly is important. In
Definitely.
hot Jupiters, there's been a lot of work on that, but the focus of this was really kind of the molecular chemistry.
Hmm. Hmm. Very good.
Um, yeah,
Okay. Cool. Always good to acknowledge previous work.
yeah.
Always a good.
Um,
Okay. All right.
so I'll give a summary,
Hmm.
section 6. So we found this three-layer structure to the atmosphere of our hot Jupiter experiencing hydrodynamic escape.
Right.
So this deep H3 plus cooled molecular layer, and slightly further up, the Lyman alpha cooled atomic layer, and finally an ionized wind layer cooled by adiabatic expansion. This reveals different parts of the atmosphere kind of respond differently to the stellar irradiation and have different cooling mechanisms. Radiative cooling in kind of in the grid and in the fiducial planet, it significantly influences the efficiency of the mass loss, departing from the energy limited scaling.
Uh-huh.
Um, and in the smaller planets, the molecular cooling can certainly, I think it's going to control the survival of these atmospheres for the smaller planets. Sub-Neptune and super-Earth outflows are much cooler
Right.
than the hot Jupiter outflows.
Mm.
Molecules survive. Molecular radiative cooling is going to play a key role, I think, and whether these planets retain atmospheres or not. Yeah,
Yes. Well, yeah. Just leave it at that. Good. Very cool. We'll come back to this point here in a bit. All righty. Very nice. Renata, beautiful work.
thank
And I
you.
want to thank you so much for walking us through your very awesome article. Thank you. Okay, and you kind of hinted at it a little bit there several times. So let me ask, where do you think we go from here, given the published article? For example, you mentioned basically putting in various metals in various forms, whether they be in molecules, atomic, whatever it may be. They're not hydrogen, helium. Um, So might that be a direction? Might there be an opportunity to compare to any observational data at some point? And just sort of next steps. Where do you think we go?
Yeah, I'm very interested in how my modeling work can make predictions on the population level. So
Okay.
I
Okay.
think one direction I could go is, like I've hinted before, pushing this model to smaller mass regimes, including metals, different compositions, more complicated chemical networks, and their
Right.
corresponding radiative cooling, and maybe seeing how this impacts things like the radius valley. Can we reproduce it with a different composition? And, what's the slope of the radius valley with stellar irradiation, for example, for different compositions? And how consistent is that with our observations?
Right. Okay. Good.
Also, I think on the observational side, I think observing UV spectra of stars is very, very useful and interesting, but I know they're very difficult to measure. So understanding how the stellar spectrum evolves with time, that would be
Ooh.
extremely
Ah,
valuable
yes, it would
for
be.
understanding the evolution of the giant planet
Yeah, yeah,
atmospheres and
yeah.
what kind of imprints the escape again leaves on a population level
Mhm.
over the planet lifetime. Definitely more observations. Lyman alpha observations are, as I mentioned, they're challenging because of the ISM and geocoronal confusion, but
Mhm.
they've been pushing these observations towards smaller planet masses. I think for this, there's a smaller than Neptune measurement, which is very exciting. So we can definitely test our theories based on that. Helium observations, what
Good.
detections and non-detections can tell us about
Mm-hmm.
atmospheric escape, and sort of, I think it's a really great complement with Lyman alpha observations.
Too.
Yeah,
Cool. Well, it'll be really exciting to see this develop over the next couple of years. It'll be fun to see.
yes,
Yeah. All righty. Renata, I want to thank you once again for walking us through your very lovely article. And that will
yes.
do,
Thank you for
everyone.
inviting me.
Sure. And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye bye.